All right, tell us who you are and where we are.
My name is Dev Avedon. I'm one of the founders and the sort of chief cook and bottle washer here at Ex Machina Soundworks, and we are currently in our demo and mastering suite at Ex Machina Soundworks proper.
And what state are we in besides the state of confusion?
Sorry, we're in Brooklyn, New York, specifically in Bushwick.
Love it. All right, so give us a little background about you first.
So I started my career in audio actually as an opera singer. I sang in the Met Opera for about 4 years, realized I was not as good as the soloists and was never going to be, but I was good at math. So I transitioned from there into an audio engineering career at first. I did a lot of mastering work for especially jazz and classical and large acoustic formats. I did a lot of recording work, some mixing work as well. And over the years doing that, having a more technical mathy background, kind of got increasingly more and more frustrated with a number of my choices that were available, and eventually found the two other smartest people I knew, the two people who were decidedly smarter than me, and was like, hey, do you want to start a company and go fix this? And they said yes. So
Beautiful. To me, it's important to be an artist or be a musician, right? So you're a singer, so you're aware of sound, sonics, all those things around you, especially when your body is your instrument, right? So I love the fact that that's where this journey started from.
oh no, it's huge. And we have a mural on the front of our building, Ebony, our chief production engineer, kindly modeled for. But on it is a quote from a Wallace Stevens poem, but it was she and not the sea we heard. And it's there specifically so that every time I come into work, I have to remind myself, like, you're not doing this for a measurement, you're doing this for the thing you're intending to reproduce.
Beautiful. Let's talk a little bit about how you came here. I remember there's something to do with the American Abbey Road idea. Tell us a little about that.
Yeah, when we first started this all out, so this building, when I originally came across it, was an old tahini factory and or tahini warehouse, and I'd been looking for a big kind of wreck of an empty shell of a space because I wanted to build a large format recording studio. That was, when I was starting this out, really my dream. In part because a lot of the really big recording spaces in New York were starting to go the way of the dinosaur. Like Solar had closed down, Systems 2 had closed down. It was hard to find the kind of spaces for tracking where you could do the kind of work that I do, like symphony ensembles and things like that. And we found this big old warehouse. We were incredibly excited about it. And the original concept of this was, we're going to make this Abbey Road for the 21st century in the sense of, like, if we need a console, we'll design and build a console. If we need microphones, we'll design and build microphones. If we need monitors, we'll design and build monitors. It was all supposed to be its own little closed ecosystem. And then a combination of, we got deep down the monitor rabbit hole and realized maybe we're onto something kind of cool that other people would benefit from. And then just the financial realities of COVID made it kind of impossible to maintain both sides of this, and came down to a choice of, you can keep one of these two things, but you can't keep them really all together. And obviously we chose to make the tools.
Yeah, well, I'm glad you did, because it's making the world a better place for audio for all of us.
Appreciate it.
Helping all of us. As I was telling these guys, a famous engineer was over at my house this weekend, I won't tell you whom, and he didn't even say, like, oh, let's see how these speakers sound. He said, let me check my mixes. And went and put his mix on. Okay, I didn't do too bad on this one.
Excellent.
He wasn't questioning the speaker, he was questioning his mix. It was amazing.
I mean, it's definitely, for me as a user of them, I do all of my mix and mastering work in this room now. And they are, I've gotten very spoiled by them, but they are also incredibly unflattering in a certain way. Like, if you've made mistakes, I shudder sometimes to go back to very old mixes, because I'm just like, oh God, what have I done?
Yeah. You are the material science guy.
Yeah, I'm so in the triumvirate of the people who do all the technical side of here. My co-founder Will is all things digital signal processing, pure mathematics. My co-founder Dimitri is all things electronics, small circuit. And I'm the physics and acoustics guy. So that comes down to driver design, cabinet design, baffle step interaction, the way our transducers behave, all of the actual moving physics parts. That's my expertise.
Killer. Let's start with the most basic thing, the box, the cabinet.
So the goal of a loudspeaker box, especially a sealed loudspeaker box, is to not move. That is its only job. If it moves, it's a driver, and the cabinet is a very bad driver. So your number one job of any good cabinet design at its starting point is inertness. You want it to be extremely stiff, you want it to be extremely dense, and then you want it to be extremely well damped, because you are always going to have some degree of coupling resonance, and you want the time periodicity of that resonance to die very quickly in the material.
The opposite of the top of your guitar or the soundboard in your piano.
Yeah, exactly. Well, the soundboard or your guitar and your piano is supposed to actually be the thing producing the sound. The speaker cabinet is not supposed to be the thing producing the sound. The driver is supposed to be the thing producing the sound. And so we choose a material called Valcromat for that purpose. It's a pultruded wood composite. So it's not dissimilar from MDF, but it's better in a lot of ways. It's a lot denser, it's a lot stiffer. But it's these long interlocking fibers instead of just chopped sawdust that's all kind of sandwiched and glued together. So you get much better damping in the material. And this is stuff that we verified with impact hammer analysis and laser vibrometer analysis. It is an extremely, extremely well damped material. So you don't get a lot of standing resonance or waves in the cabinets. They're very acoustically inert, which is what we want. And then from there, it just comes down to cabinet geometry and cabinet alignment. We can get in, if you like, at some point to why we only do sealed monitors and not ported monitors.
That was my next question, of course, because you raced right through it. You're like, well, in our sealed box. So yeah, so talk to us a little bit about sealed, because I think so many people are just used to seeing these holes in the front of their speaker, and sometimes in the rear of their speaker, and that's just what a speaker looks like. It's got these ports.
And ports do one very important thing for an average loudspeaker, and that is roughly double your acoustic output at the frequency that it's tuned at, right? Because if you think about a piston driver, what's called a Kellogg driver, it displaces a pressure wave forward and it displaces a pressure wave backwards. The ports, they're at a specific tuning so that when you get down to those very, very low frequencies, you can capture some of that back wave energy and put it back out into the room. That way it doesn't have to be capable of as long a linear excursion. You can get away with a slightly cheaper driver to design.
Mo bass is what you're going to...
Mo bass, yeah. But bad bass for several reasons. And there are reasons why I really don't like ports, and I'd rather just over-engineer the crap out of the actual subwoofer transducers. The first is port turbulence. So the air that's coming out of that port is in a tuned column, like a woodwind instrument, which means that if the velocity of that air is too low, like if your sound pressure is very, very low, it's very hard to maintain a standing column of air, and then all your low frequency energy just falls off.
Yeah, so in other words, if you're playing, you're listening to your monitors at low levels, you're not getting the same response that you are when you're playing it at high level.
that bass tuning becomes a significant problem, and you get changes in the actual frequency response of the speaker depending on the volume that you're playing it at. But that's kind of the smaller problem. The bigger problem is when you need to play loud. At some point, you will just start pushing air through that port faster than it can actually normalize to the acoustic impedance of the air around you. Like, it's got to slow down to the standing pressure of your room as it exits that port. And there are ways you try to mitigate this. That's why a lot of modern ones are flared. Some of the really fancy ones have dimples. Yeah. But you can't cheat physics at some point. You will start to hit destructive turbulence. That people sometimes call it chuffing.
Chuffing, yeah.
And it's not just that you hear that sound. It's you are destroying the actual output at that point. Like, that is pure distortion. Not good. The second reason I don't really particularly like vents and ports in designs is because it is a fixed phase relationship to the output of the driver. So a lot of what makes our loudspeakers cool is we have this very advanced impulse response correction algorithm that we developed. Has a lot of benefits we can get into in a deeper dive later. But it is still fundamentally digital signal processing. It is correcting the incoming input signal. That's how all digital signal processing works. Any change you make to that signal, if you have an acoustic port, The acoustic port is in a fixed physical relationship with the output of the driver. It's just going to move commensurately. And as a result, the output of the port, no matter what you do in digital signal processing, will always be out of phase with the output of the driver at its tuning frequency. So this thing that we're chasing of trying to have exactly right impulse response and exactly right phase response, you kind of destroy it when you put a port in there. You can't fix that.
Yeah, it's impossible. And then you can put your port in the back of the speaker, but then you create other problems.
Yeah, you can put your port in the back of the speaker, then you have fewer phase interaction problems because you've just delayed it long enough. But now you have it right up against a boundary, like you've created multiple half-wave cancellation problems. It's just really not ideal. Really the only good thing that ports do is ask your bass driver to work a little less hard for very long excursion. You can just over-engineer the driver and make it capable of that kind of long excursion, and then you don't have to deal with any of those problems. But it means that you need better drivers. Like, you're not going to get away with a $30, off-the-shelf generic low-frequency driver. Like, you need to design things that are capable of staying extremely linear at long stroke.
So in my limited experience, whenever you ask a speaker designer, high-level speaker designer, they will say a sealed box is always a better box than a ported box. And if you're looking for accuracy, it's just harder to build.
It is. I mean, it's harder to get it to play deep and loud at low distortion. The actual modeling of a sealed enclosure is, if anything, even a little bit simpler on the inside than a vented enclosure. Though obviously then the outside of the enclosure becomes dramatically more difficult because you're asking the loudspeaker to contain all of that back pressure, which is why having an extremely inert box becomes incredibly important. But it makes your driver design much, much, much more difficult, because you are asking that subwoofer driver then to do essentially twice the work.
A lot of excursion.
Yeah.
So how far I forget how far your drivers excurt.
The subwoofer drivers in Pulsar and Quasar, sort of the standard bread and butter ones, are 14 millimeters each way linear and 28 millimeters before damage. So the maximum excursion is about an inch each way.
It's incredible. Okay, so you're also, I noticed with Titan, you've got a different type of box material.
We do. Those are aluminum. And because it's a different application, right? Titan is designed for surrounds. You can also, I know a lot of people who like them as alts, like as kind of very hi-fi kind of oratones. And they serve that purpose while being true point sources, but they're more band limited. It's not the same kind of back pressure that's going back into the cabinet at that point because they're for 80 hertz and up, they're for surround applications. And so aluminum has a lot of benefits in that context for flexibility. Aluminum is an incredibly rigid material, so you get the stiffness there, but it also lets us have a design that is really nicely integrally threaded, and it keeps everything a lot smaller. You can get away with a lot thinner material for aluminum because it's unbelievably stiff. And by using an aluminum enclosure there, we can give you hard mounting points directly into the enclosure itself, so it's very easy to set them up in arrays for surround and Atmos and the like.
Great. All right, so let's move from cabinet to what's going on with the metamodal materials, and talk to us a little bit about what you're using there, because high-frequency devices, most people are familiar with, metal and, ribbon and silk.
Yeah. Well, so it's they are still piston drivers, right? So they are categorically different than like an air motion tweeter or a ribbon tweeter. Those, the entire actual assembly of the tweeter just works fundamentally differently. This is still something that you would consider akin to a classic dome driver. What's really distinct and unique about it is the diaphragm design. So if we break down in a very simple sense how a Kellogg driver works, you have a permanent magnet at the back called the motor. You've got a tube in the center, usually made out of some sort of metal, but there are advanced composites nowadays as well. And wrapped around it is a piece of copper wire called the voice coil. Your amplifier charges that because of a phenomenon called Lorentz force. You create an electromagnetic field inside a permanent magnetic field that displaces the diaphragm like shoving an umbrella out into the room. That displaces air, et voila, you have sound. Now, in this context, the behavior of that diaphragm becomes incredibly important because you want this in order to actually produce like linear frequency response without high distortion to only move in one direction. You want it to move backwards and forwards. Any way that it starts to flex like this starts to create drum modes or eigenmodes. That is still going to produce output, but it's not pistonic output. It's not essentially what you want the driver to be doing. The things you want in order to keep that diaphragm behaving nicely that way, especially as you get to higher frequencies and it has to move essentially faster and faster, is you want it to be incredibly light, you want it to be incredibly stiff, and you want it to be very, very well damped. Now, usually this is one of those cheap, fast, good triangles. Like you get to pick 2 out of the 3.
Yep.
So you can choose a fabric, in which case it is going to be very, very light, and it is going to be very well damped. Like any rocking or distortion modes are going to die quickly in the material, but it's not remotely adequately stiff. Like you're already going to be in breakup by 10, 12 kilohertz.
Yeah, so in other words, I'm not hearing what's happening above that range.
I mean, like there's output there, but it's certainly not actually linear true output.
Yeah.
Or you can pick an engineering metal. On the low end of things, you can pick aluminum. On the high end of things, you can pick something like beryllium, or you can even get really crazy and use like engineering ceramics, alumina, or on some very, very high-end loudspeakers, you'll even see diamond-like carbon. And these give you, well, not the ceramics are heavy, but these essentially give you the stiff and light part, but they don't give you the damped part. So they won't start to break up until a fairly high frequency, but once they do start to break up, there's very little to control the ringing behavior. And you'll see that, you might think like, okay, well, if it's breaking up at 25 kilohertz, I suppose my dogs are going to be upset about that, but why do I care? And the reason you care is because that breakup, when it's not controlled, shows up as modulated harmonic distortion at every octave down below it.
Yeah, falls back.
And you can see this when you take an FFT plot of something like that. There's a spike at every octave of the breakup, and it's 2-3%. And we hear that as harshness. We hear that as fatigue. The really cool thing about the TPCDs that we use, it's an acronym for thin ply carbon diaphragm. It is the raw material is called Textream. So it's a spread toe woven carbon fiber. Very different from your classic carbon fiber diaphragm in that it's not just a twill. Right? It's not mostly epoxy and then some carbon reinforcing it. That's mostly carbon by weight in these very flat interwoven, essentially sheets. And it has several benefits. One, it's unbelievably stiff and unbelievably light, like rivaling some of the best performance metals. But it is also intrinsically self-damping. So it is an anisotropic material, meaning not the same stiffness in all directions. Almost all woven materials are like this. Anything that is a fiber layout's very stiff along the axis of the fiber, much less stiff perpendicular to the axis of that fiber. Now, normally what you would do if you're doing a woven diaphragm, let's say you're using Kevlar or something like that, is you try to make it quasi-isotropic. You put the fibers at 45-degree angles so that you sort of emulate the same stiffness in all direction. TPCDs, because they are these very flat tapes and there's a very advanced automation processes for how we can lay them up, we can actually use that anisotropy to our advantage. So if you look carefully, for example, at the tweeter diaphragm, you'll see this very strange, almost like clover leaf pattern on it. And it's because that diaphragm and its shape has been exactly modeled over many, many years and many, many iterations of actual physical testing to know when it does eventually break up, which is very, very high out in frequency. It's like 38 kilohertz. Exactly how on the diaphragm it's going to begin to want to bend. And then like cutting moats in a pond, we put the weak parts of the fibers exactly at those places on the diaphragm so that they cancel and they can't ring out to the edge of the diaphragm. And that fundamentally just abates the entire first eigenmode. So you get kind of your cake and eat it too. You get active control of resonances, you get very stiff, and you get very light. You don't have to pick the 2 out of 3.
So you're taking, it's like you've got a wave on the ocean, and then if you dig a trough in the sand, now you don't have this wave anymore.
Yeah, precisely. I mean, it's not, ultimately, whether it's a fluid in air or a fluid in water, like this is all fluid dynamics. So the same way you'd think about a phase relationship in a microphone, you can think about the propagation of a wave in a diaphragm. It's just the fluid dynamics of the way a wave travels through a material.
And you mentioned doesn't start breaking up to about 38K, but of course you guys are rolling anything in that register out for us, so we don't have to worry about the fold back like you have in the metal.
I mean, like, if it's there acoustically, whether or not you're exciting it, you're going to see, you can cut off wherever you like. If the breakup is there, the breakup is there. Whether or not you're exciting that frequency, you will still see the harmonic registers of it. That's why we kind of do both. We cut off at 30K intentionally, but there's an enormous amount of research data at this point to suggest that even for transient information, so even for small timing differences that the human ears may be able to pick up as far as imaging, in perfect lab conditions with the youngest, healthiest ears on the planet, 28 kilohertz is about the absolute limit. This whole ye old school hi-fi thing of like, no, you need response out to 80K, 100K, is just not borne out by the research data. Yes, there are things, especially when you have summon differences for small timing differences, that can make a difference above 20K, but 28K is about that limit. So we intentionally limit at 30 kilohertz because if you let, beyond even the drivers themselves, if you let your amplifiers and data converters start to continue to work back out past that, you're not gaining anything that's useful to you as a human, but you are inviting like Disney radio and electromagnetic interference and all sorts of stuff that exists in the modern world that you don't want on your reproducing.
Weird shit from lighting, spurious fields. Yeah, totally.
Exactly.
Okay, makes sense to me. So we've talked about the high frequency device, but it's nested. Why do you have a coaxial design? And tell us about how all that goes together. And
the short answer is because power average. And the long answer is, it is one thing to design a loudspeaker that has a very nice linear response in one place. That's not how humans work. That's not how humans hear. Like, even if you were to stay stuck in one spot forever, like with your head in a vise, which nobody wants to do, like you've got your preamp in the rack over here and your EQ up here, like you move around your control room.
Well, you don't want your client, come sit in daddy's lap and listen to your mix.
Yeah, that doesn't work.
It's like you want to sit here and enjoy it, and you're supposed to move to music. Even when you're mixing, hopefully you're getting, inspired by it and you're actually moving to the music.
100%. I mean, like one of the things I hated the most, back in the days before we started to design stuff, when I had sort of more traditional two-way loudspeakers that had very distinct lobing angles, like, okay, everything kind of worked here, but all the top end fell off if I moved a little bit this way, is the kind of dolphin dive thing where you duck down, make an EQ change on like the 1073s over here, and then like kind of pop your head back up. Yeah. It's just a very unpleasant way to work.
Yeah, for sure.
But even just in terms of the way that you're going to hear sound in a room, like, yeah, some of that's direct energy, but some of that's reflected energy. You're in a room. Your brain is much more responsive to power average, like to the average of the way the speaker throws energy into the room, than it is to frequency response in any one given axis. So the really nice thing about a coaxial loudspeaker, a coincident source, is that it is a point source. You don't have a difference in physical space when, like the relay race, you've got to trade off from the tweeter to the woofer or the tweeter to the mid-range. And you will, no matter what you do then in digital signal processing, there's always a physical difference between those two things. There will be a handoff point where you can kind of get it right pointing this way, but then it's not going to be right pointing this way. It's just laws of physics in that regard. With a coaxial design, everything comes from a single point in space, so it is inherently in time.
So yeah, so your ear is here, you don't have your high frequency here and your mid-range here, you've got them coming to your ear at the same point in space.
Yes, and it's also how they sort of trade off, again, like the handoff in a relay race. Your brain's not going to be that sensitive to, say, like the middle octave of what your woofer is handling and then like the middle octave of what your tweeter is handling. But at that point where they're trading off and some of the energy's coming out of the woofer and some of the energy's coming out of the tweeter, because your crossover is not a brick wall.
Yeah.
There's a point where they're both playing at the same time. That point's usually somewhere between 2 and 4 kilohertz. That happens to be right in the middle of the range that the human ear is the most sensitive to. And there you get a lot of problems.
Yeah, that's what typically, coming up with passive monitors, you had the Tannoy that had the scoop in there, and you had the Yamaha that had the bump in there or whatever. It's like you could just look at the frequency response curve and you knew that was the crossover point, where there's some issue.
Yeah, and you're still going to get that even a little bit with a coaxial design in a vacuum, but that's why we have fancy digital signal processing. Essentially, your crossover introduces two problems. In a traditional loudspeaker where you've got physically separate devices, now you have to change the actual lobing angle and the incidence of the sound in a physical point in space where it's crossing over. And then you also have the electrical group delay of what the crossover is doing. We solve the physical aspect by having everything come from one point in space, and then we solve the electrical aspect with digital signal processing.
Great. Okay, so tell us a little bit about the design of the mid-range in terms of the spherical waveguide, how that works for us.
So one of the really beautiful things about using this thin ply carbon diaphragm material, for the tweeter, for the high frequency device, it's great. It just gives us the anchor of our relay race in this now tortured analogy, to be the fastest guy that goes out to infinity and beyond in terms of its behavior. But it then also lets us do things that we couldn't get away with poorer behaving materials in terms of how that mid-range is shaped. So when you're designing a cone-shaped diaphragm, generally the steeper the angles, this is a bit of an overgeneralization, but generally the steeper the angle, the more stiff you can get the actual geometry of that to be.
The physical stiffness of it.
Exactly, and you need that stiffness because you don't want the mid-range to start to beam too early, like you don't want it to start to roll off its response off axis too early, and you don't want it to break up too early. The problem with that is that the ideal geometry for stiffness is not the same thing as the ideal geometry for a waveguide. And as a result, it's not actually loading the energy into the room the way that you want it to. Like, you can take advantage of the fact that you have essentially a high frequency device embedded inside of a mid frequency device, and you can make it like an optimal waveguide that throws this really ideal 90 by 90 coverage angle. The reason we're able to choose a geometry, and it's an oblate spheroid waveguide, like this is pretty known math. There's nothing really crazy about that aspect of it. What's crazy about it is that it's an oblate spheroid waveguide that moves. Like, that is not a geometry with almost any other material that you would be able to get away with. It just wouldn't be stiff enough. But because we have this ridiculous space age material, we're able to still keep the mid-range behaving as a piston 2 octaves above its crossover point and shape it optimally for waveguide behavior instead of optimally for stiffness behavior. And then the other aspect of what kind of makes our coaxial really special is the surround design. Because it's a pretty large driver for a mid-range, like it's 6.5, 7 inches, it has a lot of radiating surface area. This is another thing usually for mid-ranges you can't get away with, because it's the larger you make the driver, the lower it wants to break up in frequency, and it's a mid-range. You need it to kind of get up into the mid-range. But because we have this very advanced material, we're able to get an enormous amount of radiating surface area, and that gives us 2 benefits. One, it means that the actual mid-range is large enough to be an effective waveguide for that tweeter, and it does. It behaves exactly how you'd want it to.
So let's explain waveguide for people.
Right, so think of this as kind of a horn, but the point of it is not to make things louder. It's to make the way that that energy, especially at high frequencies, especially as wavelengths get short, essentially the same within the entire coverage behavior. So you can think of it just like putting your hands up to your mouth.
Yeah.
The shorter those wavelengths get, the more they will interact and behave with acoustically large objects to them around them.
Okay, so we were talking about spherical waveguide. The first time I was exposed to one was with Panasonic Ramza, and they had put one in a PA box, and they had me talk into first a normal horn, which sounded like this, right? And then they had me put that normal horn up to my ear, and it sounded like I was listening to the ocean, like a seashell. And then they had me put their spherical waveguide up to my mouth, and it just sounded like I was speaking normally. And then listening back, I could also hear the world normally.
And this is exactly the point of why you'd choose an oblate spheroid waveguide. Because you can choose one of 2 things with a horn or a waveguide design. You can get loading, like you can get more acoustic energy, or you can focus entirely on coverage. You can focus on dispersion behavior. And that's, in the least kind of technical mumbo jumbo sense of the word, that is the point of the shape of that. It is to take what would naturally, if you just took that tweeter and stuck it on a plane and left it alone, it would beam. All devices beam eventually, no matter how well you shape them, any Kellogg device. And by beam, it means like, you'd get nice, even coverage, like the same amount of power in mostly every direction up until a certain frequency, and then it starts to narrow. You get tighter and tighter and tighter and tighter. And if you've worked on kind of like an old school traditional loudspeaker that just has a tweeter on the baffle, I'm sure you've experienced this before where you sit up and all the trebles go on. And everything suddenly gets very dark and murky. Yeah. That's the point of why you want a good waveguide design, is so that as you get into those treble frequencies, as you get into those higher frequencies, the energy stays fairly constant as you move around. And it will obviously roll off eventually. There's a physical limit to everything. But for ours within that, when we say 90 by 90, we mean a cone that's about a 90-degree coverage angle, which is, I think, a very good.
Generous.
I think it's a good shape for physical work. You don't want, in my opinion, you don't want a perfectly omnidirectional loudspeaker because you're in a room with walls with reflection issues.
Of course.
That 90 by 90 angle, I think, is really ideal for most working environments. And within that 90 by 90 coverage angle, way up to about, I think, like 18 kilohertz, you're still plus or minus 3 everywhere within that coverage angle.
Yeah, amazing. So that allows you the ability to move around like we started this conversation with, and actually exist as a person, feel natural in your movements, and move really close to the speakers, move farther away, stand up, sit down, do all these kind of things.
Yeah, exactly. And you don't have to get quite so neurotic about setup either. If you've got, if you're setting up for a session relatively quickly and the toe-in's not exactly perfect, or you're not exactly in an equilateral triangle, it doesn't really matter. Like, they're very generous and very forgiving in that regard.
Cool. So the material science you've taken, you've examined everything, the cabinets, the drivers, all these different parts of the box, and you've taken that as really as far as we can today. Like the metamodal materials, where do we find those? Where are they where they exist in other things?
Well, it's specifically engineered. Like, we come down to its atomic elemental level, it's carbon. It's high modulus carbon. It's, for me, the final frontier of this is not chasing for adamantium somewhere out in the universe. It's taking the strongest materials we know to exist and then figuring out how we can engineer and construct them and put them together so that they perform more than even the sum of those parts. And that's the thing that makes me really excited about TPCDs and about this technology, where it's as much about the weave and the geometry as it is about the raw material itself, is we're maybe in the first 20% of what's possible with this. Like, as time continues to go on and our automation gets more advanced, our modeling gets more advanced, like, this same material will get better and better and better. And it's already better than almost anything else out there.
But it's in things like the Endeavour blades, right?
Yeah, the Mars Ingenuity rover, so the little tiny helicopter that they made for the last Mars mission, where it has to actually achieve flight in an atmosphere that's 1/100th the density of our own atmosphere. This raw material is what they chose for the rotor blades, where you need as good sort of performance to weight ratio as you can possibly get.
This type of material, as I understand, is something that's sustainable, right?
It is, because it is just raw modulus carbon. I mean, carbon's an incredibly abundant element in both our planet and in the universe. And the other nice thing about it too is, the thing about thin ply technologies is that it is more sensitive to the actual layup and weaving process. You could use this same core technology with anything basically that can be flattened into a tape. So you could do it with, Dyneema or Spectra or, advanced polymers. The actual carbons that we use, are all wet spun carbons. We use, this will get very technical, but we use very few polyacrylonitriles in their actual pultrusion for spinning them. The non-crazy technical version of this is, it's raw carbon, and then we also source the carbon in a way that is not nearly as industrially damaging as kind of traditional carbon fibers.
So we'll probably see this down the line, like you're talking about, we're at the edge of it. We'll probably see it in the blades of windmills or something like that.
I mean, it would make a lot of sense for that application, especially when you consider that, for wind power, the constant fight and trade-off that you're playing is in order to get more efficiency, you need longer and longer cord length. And the longer and longer cord length you get, forget even the structural integrity of it. Think about the harmonics of that longer and longer cord length. Having a material where you can actively control that harmonic behavior in the cord length, and then it's also stronger, it's lighter. Yeah, I think it makes an enormous amount of sense for this. This is one of the big drawbacks of wind power right now, is that with these kind of classical fiberglass assemblies for these bigger and bigger blades, they're nigh impossible to ship, and they're nigh impossible to recycle. Like, you're designing things the size of a tanker truck that have to withstand hurricane force winds. What the heck do you do with them when it hits the end of its life cycle? And so a material like this, I think, could be incredible for wind power.
Great. So let's keep talking about sustainability for another second, I guess, because even the Velcro mat is a better material in terms of green than using something like MDF, right?
It is, for several reasons. It's an all FSC certified material, which Forestry Stewardship Council means there's a guarantee in the actual wood product that goes into it that it is all rapid renewable forest, that none of this is destructive to forestation. The other aspect of this that I think is very important is it's an all zero VOC material. There's no kind of toxic urea or formaldehyde-based glues that are in it. It's both in terms of a manufacturing perspective, from the health of the people working on the material and the kind of industrial output that comes out of it. It's much less toxic, and then in terms of its actual net end use and recycling, it's much less toxic. That goes then as far as the way that we do actual finishing as well.
Yep.
We don't do kind of traditional lacquer coats or things like that. We don't do the kind of spray paint applications that do have a lot of volatile organic compounds that are fairly toxic. We use an all-natural oil-based finish called Rubio Monocoat. Again, it's zero VOC. It's incredibly safe.
Great. All right, so you've taken your material science now, and you've pushed it to the limit. We've got things going around on Mars utilizing some of the types of materials. And so now how do you actually go beyond the physics of the materials and take it to the next place?
I mean, I think that's where we come into digital signal processing. And I am going to now attempt to speak for Will here, and hopefully he will forgive me if I get this slightly wrong.
Give us a little background on Will first, and then...
So Will, one of my co-founders, he's our pure math and pure DSP guy. He's crazy genius. He worked on the LIGO project before he worked on this, so essentially studying large gravitational waves in the universe. And one of his many contributions to the cool stuff that we do here is he developed a brand new impulse response correction methodology from scratch. So this is not like what you'd get in like Room EQ Wizard or something like that. This is not just a...
Not off the shelf.
No, this is a completely new mathematical process starting from a blank sheet of paper. I can't talk exactly about how it works because it's kind of our special sauce, but I can say that it has better latency for bandwidth relative to other impulse response correction applications. It introduces dramatically less pre-ringing. So normally when you do anything in a finite impulse response filter, or anything linear phase, and I'm sure a lot of engineers are familiar with this with like linear phase EQs, to make something linear phase, you end up taking like the ringing at the end of the filter and you push part of it to the front. Ours does not do that. And then it also doesn't double ripple or magnitude errors. A lot of traditional impulse response correction approaches, like small ripple errors, get doubled in the way that they're summed. Ours does not do that. And the benefit of that then integrated directly into a loudspeaker is, yes, you can get transducers that behave incredibly well. Yes, you can get physical acoustic coverage angle that behaves incredibly well. But there will still be magnitude deviation in even on axis naturally. You're still essentially shoving a very fancy piece of carbon to a tube and asking a magnet to shove it back and forth. And there will be necessarily group delay. At any crossover point where you transition, like that filter has delay. Now you can try to use a linear phase filter and just avoid the delay, but then you run into the pre-echo problem where you get those ghost transients ahead of the real transient, and you really don't want that. It would defeat the purpose of having these incredibly fast transient materials. So our process essentially takes a raw snapshot of the loudspeaker, just how it behaves acoustically, and then through a long and convoluted process, then like getting a new prescription for glasses, develops an exact filter that when combined with the original signal gives you exactly flat phase response and exactly correct magnitude response for the calibrated axis and exactly correct impulse response. So you get these incredibly fast transients, you get everything starting at a very linear frequency response, and you get everything exactly in time. Across the whole bandwidth of the loudspeaker, we get no more than about 5 degrees of phase rotation, 20 hertz to 30 kilohertz. So everything then arrives to your ear at the same time. There's not delays at different frequencies that you can hear as kind of blurring and smearing.
Everything at your ear at the same time, incredibly quickly.
Yes, so. And the impulse and the transient response you can see when you do more advanced excitation measurements. Like if you go beyond a log chirp and you start to do like Linkwitz multi-tone testing, or we even have an Audio Precision 555 series where we use their tone burst generation. It's essentially a single cycle of a single waveform, and we can damn nigh reproduce that acoustically, which I defy you to find much in the way of anything else that can.
Yeah, so let's break that down, make it simpler for people. So you've got your speaker in your hemianechoic chamber, you've got your test microphone in front of it, you send a signal from the Audio Precision to the speaker, right? And you record that.
Yes.
Okay, and then you overlay what it just played back on top of the original waveform, obviously dealing with amplitude, and you're getting the same thing back.
As close as you're ever going to see out of an acoustic excitation. So your reference point is the electrical loop back on the generator. Maybe you're reproducing a square wave, maybe you're doing these more advanced things like this kind of single cycle tone burst, but your reference point for what it's supposed to look like is just inside the Audio Precision analyzer, just going through a couple of electrons. And that's your reference signal for like, okay, this is say a single cycle tone burst at 1 kilohertz. Square waves are a kind of classical way of doing this, where you get the electrical back and it should be these very sharp transitions. And then you play that back through a loudspeaker and it's not. It's this kind of vaguely somewhere between a sine wave and a square wave because it's a driver, it has momentum. It has differences in timing accuracy. With ours, you really can put in a 1 kilohertz square wave and have less a tiny little bit of ripple at exactly the transitions, which is, it's still a physical thing that moves that has momentum, but I mean, it's minuscule. You get a square wave back.
Yeah, so you're talking about the driver, to make a square wave, a driver has to go out almost instantly and then back almost instantly.
Yeah, which, it's still a physical thing that moves and it has momentum. And
it's
that's
like your car. You can't just jam on the gas and then jam on the brake.
Yes, there will always be, no matter what you do, some degree of start-stop time.
Damping.
But our settling time is nigh instantaneous. We've been working actually on variations of our software for test and measurement applications, seeing just how far we can push this. And we see settling time in under 2 milliseconds.
Incredible. So what you're achieving is greater clarity because it's this reproduction of what you're actually capturing. Now you're able to put it out there in the world, so you're able to mix and determine how that should translate elsewhere. Ultimately.
Well, and that transient behavior really shows up. I mean, if you think about it, there's more to modern mixing, than just like an EQ decision or a distortion decision, all of which having a very low distortion and very linear loudspeaker is great for. There's also an incredible amount of transient information that's important, whether that's by way of gating or side chaining or transient design or compression. A lot of what gives you dynamism and punch and things that make a mix exciting is the way that transients behave. Having a loudspeaker that can actually reproduce kind of whatever crazy thing you want to do with the transients in your mixes is a very valuable tool in terms of insight.
Yeah, I mean, you can also, I'm always listening to stuff and I hear mistakes. I hear things that people didn't realize were there because the speaker didn't actually let them know.
Yeah, and I mean that's a big thing too. Like I will also not name any names on this, but I've listened to some like, big name top 40 mixes where you'll play them on these. You'll play them on like a set of laptop speakers, and it just all sounds kind of fine and fuzzy and loud and generally glossy the way a lot of top 40 stuff is. But then you play it like through our speakers and you'll hear like the L2 or whatever maximizer they were using warbling and intermodulating in the middle of a vocal line in the chorus. And it's like, how did this go out the door?
Yeah, I mean, I was even listening to a Van Morrison track from the 2023 record, and I'm just working, right? This is background music, right? And all of a sudden the guitar solo comes in, and I jumped out of my seat. I thought something terrible had happened in the house, but it was all this low frequency content that hadn't been removed.
Oh,
this
gosh.
acoustic guitar solo was like whoa, 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 from the mic stand moving or whatever, and I thought the world was coming to an end.
Yeah. I mean, like you'll see that in terms of like low frequency energy. You'll see it in terms of like phase relationships are the biggest thing. That's when you've got really badly mixed, like especially left side of stereo image, it feels suddenly like physically nauseating.
Yeah, it's remarkable. Okay, so tell us a little bit more about the DSP, for example. It's pretty potent. Like I noticed when I boot up the speakers, it takes like 45 seconds or something for them to...
Yeah, and that's because like we need processing power and memory to do all of the ridiculous stuff that we're trying to ask it to do. So it's not a kind of traditional Sigma DSP. It's not like a cheap fixed point kind of thing. There's an individual 5th generation Shark Plus DSP processor in each loudspeaker that's like 2.5 cores on an Apollo, basically. And we need all of that processing power in order to get the kind of granularity that we're getting.
Yeah, amazing.
We do also pay a lot of attention to the quality of the data converters. I think sometimes that could be a thing where, people have data converters that they, DA and AD converters that they really care about and really like in a rack. And then it's a DSP powered loudspeaker, and because it's embedded into the loudspeaker, they kind of forget to ask. But we're not using kind of cheap system on chip stuff. It's, top of the line AKM discrete converters. It's like 5572s on the incoming side and 4493s on the outgoing side, which, is the top of the discrete range. Not the very, very top, it's like 4499s or something ridiculous like that. But, these are high-end discrete data converters.
Yeah, it's beautiful stuff. Address the latency, low latency, and high latency mode for people so they understand why and what they get. And
yeah, I mean, like, so in the full cal mode, that's where we're doing all of the phase magic and the impulse response correction magic. And in order to change the timing response of a loudspeaker, you need to be able to look a little bit into the future. Like, it has to know what's coming. And so in order to get that across all of the frequencies that we care about, we need about 46 milliseconds of input latency. Not nearly as crazy as it can be for other advanced FIR deployments. That's still, in my experience at least, like that's still not really noticeable for editing unless you're doing like very precise Foley work or something like that. It's not really a problem for mixing. But it definitely is a problem if you wanted to track in the room, like you wanted to lay down especially a DI'd part, like a bass or something like that. So we do also include a low latency mode, and that's very low latency. It's about 3 milliseconds of input latency. And that disables the phase correction. It just does magnitude correction, just as frequency response correction. So not quite as accurate as the full calibration mode. Won't get quite the same magic in terms of the imaging, though still very good because it's still a physically, acoustically good object. But that's appropriate for if you need to make live tracking decisions.
yeah, I mean, to me, it feels like you instead of just making a box that's kind of messed up and then trying to fix it with DSP, you made a box that's exquisite, taking it as far as you can to make a perfect box on its own, and then use the DSP to propel it beyond that.
Well, we also thought about these things from the beginning in tandem. So we knew what we could address with DSP and what we couldn't. Outside directly harmonic distortion behavior, which you can do some stuff with DSP to address, but you're certainly not going to do anything about sideband or intermodulation distortion or complex distortion. and power average, like you can't get DSP to fix those things. So when we looked at these drivers, it's like, all right, let's optimize them specifically for the things that we cannot get DSP to adjust for, and then let the DSP handle the things that it can. A perfect example of that is power average and the way that the waveguide behaves. Like, I can linearize a signal to whatever average I want, but how that changes physically, acoustically in the room as you move around it is how it changes physically, acoustically in the room, unless we're doing some, insane beam forming line array. And so we think of these things as working in tandem, not one per se trying to fix the other. We focus on acoustic solutions where they're the most appropriate solution, and DSP solutions where they're the most appropriate solution.
Makes complete sense to me. Man, so you've taken it this far. I'm in love with the stuff. I've been using it since 2020. Is there anywhere to go beyond this, or is this it?
No, there's always somewhere to go. That it's the greatest thing for now is the greatest thing for now, and we're always trying to technologically innovate, whether that's like at the actual production level. So I'm actually directly involved with Composite Sound, the company that makes the TPCDs, and we're constantly working on trying to see how much more we can squeak out of diaphragms for the future. There are things like I have my wish list in terms of connectivity and feature set, and we're all working on those in the long run of things too. And then we're also, I can't get hugely into it yet, but we're also starting to dip our toes into things beyond just loudspeakers, and that's all I'll say about that for now.
I'm excited. I'll be watching. Cool. All right, brother. Well, thanks so much.
Great to see you as always, Mark.